In the last part, we have looked at what are the effects of notch present in a sample, and we have seen how notch will affect the stress field ahead of the crack tip. In this part, we'll be looking at how the cracks which have plastic zones ahead of the crack tip are modeled. So for that, let's consider this sample which has a surface crack of length A, and let's mark coordinate axis like R here ahead of the crack tip and sigma yy, that is a stress along yz direction. And let's say if we don't have plastic zone ahead of the crack tip, or let's say material is elastic or a very brittle material, you will see a stress field ahead of the crack tip to be varying in this fashion, where you reach a very high value of stress just ahead of the crack tip. We have seen this in earlier part. Now let's consider we have a plastic zone which has a diameter of Rp ahead of this crack tip. This will happen when the material deforms plastically or material is plastic or ductile. So we can see that for this kind of material which shows a plastic zone ahead of the crack tip, the stress variation will be sigma y. So you will have a variation sigma y, where sigma y is nothing but a yield strength of a material. So the stress ahead of the crack tip remains constant, and such kind of materials are called as elastic plastic materials. And when this plastic zone ends, the stress varies or decreases in this fashion with respect to R. Irwin has described this kind of elastic plastic materials using a model, and he considered this radius to be A effective, where A effective is nothing but this crack length A and Rp, which is nothing but diameter of this plastic zone. So we have A effective, which is considered to be A plus Rp, and this Rp can be found out by using this radius R1, and this Rp is almost equivalent to twice of R1. If you consider this material to be elastic, you have the stress field variation with respect to R in this way, and when you have elastic plastic material, you have stress field variation in this way. So where this point intersect, that R is nothing but your R1. So here R1 is a location where this elastic stress becomes equal to sigma ys, that is yield strength of a material. And that is how you find out R1, and from R1 you can find out what can be the plastic zone material, which is nothing but equal to twice of R1. And Irwin considers that A effective, that is an effective crack length, to be equal to A plus R. Now this is nothing but a fictional crack length. If you consider a theory, this model considers a longer crack length, but it takes care of a stress field. So you can see that the stress field will be taken care. If I consider this a crack to be of this length, that is A effective, it can take care of stress field ahead of this plastic zone. And also importantly, that this Rp is found out with many iterations. Now based on this, Duc-Dallais has proposed a model which is very useful. So in that model, he considered this crack length of 2A and the plastic zones of length R and R on both sides. So you have effective crack length. Let me write that down. So if you have an effective crack length here, can be written as twice of A plus R. And what Duc-Dallais considered that this plastic zone blunts this crack, and it can be considered as there is a compressive stresses acting on this region of R, which is nothing but a plastic zone. So we have an effective crack length of 2A plus R, and this on this R part you have a compressive stresses, and based on this assumption, this R can be found out to be equal to pi k square upon 8 sigma ys square, where sigma ys is the yield strength of a material. And you can find out what can be the length of this plastic zone using Duc-Dallais models. I'm not going into derivations of it. It's given in a mechanical metallurgy book by George E. Dieter, so you can refer that. Now let me introduce an important term when we talk about elastic plastic materials, that is a crack tip opening displacement. So for that, let's consider this as a crack, and let's consider a plastic zone which is ahead of this crack tip. Now let's consider this crack of length 2A and the plastic zone of length R. And let's consider this crack is subjected to a mode 1 fracture, and let's mark our coordinate axis, that is x along this direction and y in the vertical direction. Let's consider this is to be a root radius of a crack, that is rho, and this distance delta is called as crack opening displacement. So when you subject this crack or consider this crack under a mode 1 condition, this delta will increase. Let me mark that over here. So when you put a force in mode 1, you can see that this delta tends to increase. And this is why it is called as crack opening displacement, because this crack will open. Now this delta small del is called as crack tip opening displacement. So you have this crack tip, and when I have put this crack in mode 1 fracture, you can see that this del also will increase, and this is called as a crack tip opening displacement. Now what you can consider that this is a plastic zone. So ahead of this crack tip, you can consider that there is a tensile sample or specimen ahead of which has dimensions of length L and width W. So you can say that when the force is applied, this sample, that is a tensile sample, will experience some kind of a plastic strain, because this lies in the plastic zone, and that's why this sample will elongate, and that is how this delta is modeled based on this strain developed in this tensile sample. So this is an imaginary situation or just a thought experiment that there are series of this kind of tensile samples ahead of this crack tip which can represent this plastic zone. Now, when this sample breaks, it passes a strain on the next sample like this. So here you can consider another sample, and when this sample breaks and it causes a fracture in the next sample, in such case we call this crack to be unstable. When this sample fractures but it doesn't cause any fracture in the second sample, such cases called as a stable crack growth. So let me write that down. So you have these samples. So sample 1 causes fracture in when sample 1 causes fracture in sample 2, this is called as unstable crack growth. So when sample 1 fractures but doesn't cause any fracture in sample 2, this is called as a stable crack growth. So we can find out this using a crack tip opening displacement, and an important relation we can find out when this crack propagates in a stable way, that's the strain energy release rate, that G is equal to sigma ys, which is nothing but an yield strength, and this del, which is nothing but a crack tip opening displacement. So you can refer George editor for finding out how this relation comes. You can use Dugdale models, which we have figured it out what can be the R in front of sigma ys, and based on these relations you can find out what can be the strain energy release rate. And this is an important relation where G is equal to sigma ys, which is a yield strength of a material, into del, which is nothing but a crack tip opening displacement. Now let me move on and introduce two fracture mechanics when we try to understand a fracture in materials. One is linear elastic fracture mechanics, another is elastic plastic fracture mechanics. So this linear elastic fracture mechanics works very well with brittle materials we have already looked at, and a material which has a very high strength, like more than 1400 MPa. For such kind of materials you can comfortably use this linear elastic fracture mechanics. However, when the material deforms plastically or materials are ductile, you should use elastic plastic fracture mechanics to understand the fracture behavior of such materials. Now let me explain it to you that what is LEFM. So let's consider you have force and displacement of this crack. So let's say you have material of or a sample of thickness B equal to 1, and you have a crack, initial crack to be of length A. So in such cases, the crack will displace when you apply or increase a force linearly in this way. That is why it is called as linear elastic fracture mechanics. So the displacement has a linear relationship with the force. Now let's say you have a crack A plus delta A, a small increment in this crack length, that is to be delta A. And we have seen that the force to extend such cracks which are slightly bigger than this crack will require a less amount of force. And the energy which we get here in between, we term it as G into dA. We have seen this. So the difference between these two will give you the quantity of GdA. dA is nothing but a small increment in the crack, and G is the strain energy release rate. Now when we look at this elastic plastic fracture mechanics, we also plot force versus displacement. But however, in this case, the variation of force with displacement is linear, In this case, when we consider elastic plastic fracture mechanics, you will not have the linear relation. Let's consider the unit thickness of the sample to be 1, and you can see that for a crack length A, the force displacement relation is not linear. Now let's consider a crack length of A plus delta A. Here also the force displacement relation is not linear, and the energy release that can be given as the area between these two curves, that is called as J into dA. Here J is nothing but a non-linear strain energy release rate. So the linear strain energy release rate we denote it by G, whereas non-linear strain energy release rate we denote it by J. And this J comes from the name James, which is a name, the first name of James Robert Rice, who is one of the famous scientists from Howard University, who has proposed how to identify this energy when you have a non-linear variation of force with displacement. That is when we consider elastic fracture mechanics. So he has contributed to the concept of J integral. So this J has comes from this James Rice, and this G has come from the name Griffith. So with this introduction, let's understand what is J integral. Now we have to find out what is a non-linear strain energy release. So let's consider this crack, and let's consider this as X direction and this as a Y direction. These are our coordinates, and let's consider this line which is given by gamma, capital gamma. So to find out J integral, that is a non-linear strain energy release rate, we consider or we do it by finding out a path independent line integral. So we consider this as to be path. Let me mark it over here. So what we are doing here, we mark a path over in this way, and we enclose this crack with this line, and that is why I mentioned that this is a line integral to find out what is a J, that is nothing but non-linear strain energy release rate. Let me mark or write that down also. So J is nothing but non-linear strain energy release rate. Now we'll go with the same methodology how we found out G, that is a linear strain energy release rate. So let's consider this to be a 2D approach. Consider the thickness to be equal to 1, and we find out J to be equal to minus du naught upon dA, where when this crack extends, there will be release in the strain energy. So that we call it as release of potential energy per unit crack extension. That you can find it out by using this integral, line integral over this line segment, that is gamma. And when you know that when the crack extends, there will be a release of strain energy. Also, you have to do some kind of a work which is given by this. This total value will give us the what is a change or a release of potential energy per unit crack extension. So this term will give us the strain energy per unit volume due to loading. This gamma, which is nothing but this path, and this path must enclose this crack. So this is the path of the integral which encloses the crack. This is a T, which is nothing but a traction vector, that is a force acting on this crack on this path, small path ds, which is nothing but an increment of the counter path. So when we consider this small path and we try to integrate for a whole path of gamma, and this T del U upon del X into ds gives us the rate of work input from the stress field into the area enclosed. So when this crack extends, there will be a release of the strain energy, and there will be a work done form a new surface, or there will be an increase in the energy to form new surfaces, or that can be amounted by considering this rate of work input from the stress field into the area enclosed. So what is the energy required or work input which causes when the crack extends? And when I say it has to be path independent, what do I mean by that? So I can consider any path. Let me mark that also. So I can consider this as my path. Only criteria is that this should enclose this crack. So I can move around like this and I should enclose this path. I can consider another path, something like this, which is a dimensions of samples itself. So you can consider this path as well. This is a path independent integral, and the value of j will not depend on this path. That's the utility of j integral. I'm not going into details of it. So we can find out the value of j to be equal to k1 square upon e dash, where e dash is but e, which is nothing but a Young's modulus. When we consider a plane stress condition, e dash is equal to e upon 1 minus mu square, that is in the plane strain condition. So what is relation between j and crack tip opening displacement? You can find that out as to be j equal to sigma ys into delta. You can refer any standard textbook to find out how to find out this integration. Let's say you can just use this reference mechanical metallurgy by George Dieter, and you can see to yourself that j has this value. Now, in earlier slides, we have seen that G is equal to sigma ys into delta, and what does it indicate? So it gives you a most important understanding in fracture mechanics that J obtained under elastic plastic condition is numerically equal to G obtained under elastic condition. J is what? J is non-linear strain energy release rate, which you get it from elastic plastic condition, is numerically equal to G, that is a linear strain energy release rate obtained under elastic condition. And based on this, we can identify what can be the J at different conditions of stress, that is plane stress and plane strain conditions. Now, let me give some of the terminologies which are used in the literature. Let's say when we consider a brittle fracture and a ductile fracture. So there are three ways based on which a fracture terminologies are used. So let's say crystallographic mode. So when I talk about a crystallographic mode, I call brittle fracture as a cleavage fracture. So when I talk about cleavage, what I mean is that I'm talking about some crystallographic directions or planes. And thus I call such kind of fracture, let's say if I call it as a cleavage, that means it is a brittle fracture. If I call it as a shear, it is a ductile fracture. Now on the appearance of fracture, you call it as a granular or a bright. So when material shows, like let's say you see a fracture surface and you see a granular or the surface is bright, you can consider that the material has failed in a brittle way. And if it is a fibrous or a dull, you can call it as a ductile fracture. Now, based on a path, you can call intergranular fracture as a brittle fracture, and a transgranular fracture or an intragranular fracture occurs in a ductile materials. So let's understand this. So when I say cleavage, I'm talking about a crystallographic mode. And here when I talk about cleavage, it's a brittle fracture. You can see here that this represents a brittle fracture. And here in this case, you can see that it is intergranular. You can see that here it is moving from grains to grains. In case of ductile failure or ductile fracture, you can see that there is a transgranular fracture, and these are the voids which will form, and it forms naking over here, and there will be shear localization when you have a ductile failure in a material. So let's understand these two terminologies, intergranular and transgranular. So when you have intergranular fracture, it occurs in a brittle way. When you have transgranular fracture or a path, it occurs in a ductile way. Here we have a transgranular or intragranular fracture. So you have these grains in a polycrystalline material, and this is a path of crack propagation, and this path of crack is passing through grains. So it is kind of intragranular, so it is passing through grains, and that is why we call it as intragranular or a transgranular. However, in this case, the path of crack propagation is through grain boundaries. It's not through grains, so it's through grain boundaries, and this kind of fracture is termed as intergranular fracture. And these are the typical micrographs which indicates a transgranular or intergranular fracture. So you can see that the crack would have propagated through boundaries. You can see here that it is propagating through boundaries. However, in this case, you can clearly identify that the crack would have propagated through grain. In this case, you can say that the grain refinement improves both strength and fracture toughness of material. So as you can see that if I have finer grains, the crack will take a longer path. along grain boundaries, and thus grain refinement improves fracture toughness, and we have also seen that grain refinement improves the strength of material. Now let's go on and try to understand how we can design a material to resist fracture. So the first thing is like avoid sharp cracks. We have seen that if the cracks are sharp, there will be triaxiality or there will be a stress concentration ahead of the crack tips, and thus there will be chances that material will fail in a brittle way or a catastrophic way. Another important thing when you try to design composites, use small fibers over large fibers. So let's say you have these two conditions where you have small fibers in matrix and these are the large fibers in this matrix. So you can see that if there is a delamination happening, let's mark over here, let's say there is a delamination over here, so the crack will typically have the length of this D. So the largest crack will be greater than this diameter of this fiber. Let me write that down also. So your crack will be somewhat similar to diameter of this fiber, and thus if the crack length is higher, the material will fail at lower stresses also. That's the fracture toughness goes down. So when you want to design a material, you should always design having a small fibers. So this design criteria considers the shape and size of these fibers. So shape, we have talked about that we should go for a smaller fibers in such a way that it should not create any stress concentration. So you should not have fibers which have a sharp tips. Let me write them down also. So fibers, no sharp tips or sharp edges. Now let's consider a composition of steel. Steel is used widely for many structural applications. So when you design a steel composition, so it should always have lower sulfur content. Why? Because it forms iron sulfide at grain boundaries, and it should have higher manganese content because it forms MnS globules. Let's understand this. So when you have higher sulfur content, so this forms FeS, which has a sharp edges or sharp precipitates which forms at these grain boundaries, and thus this FeS makes these grain boundaries susceptible for crack propagation, and thus it decreases the fracture toughness of a material. So any phase which are at the grain boundaries which are brittle, this FeS is also brittle, which increases the stress concentration and thus makes this material susceptible for crack propagation. This FeS acts as a location for crack nucleation and propagation itself. So if you have more amount of sulfur, it leads to more amount of iron sulfide at the grain boundaries. And you might be remembering the case of Titanic. So when the Titanic was made, it had supposedly a large content of sulfur. And because of this sulfur content, there may be a formation of this iron sulfide at the boundaries. And when it hit on the iceberg, this material causes a crack formation at these boundaries and it catastrophically failed, and that led to a tragic accident. Now, how to deal with such situation when you have a large amount of sulfur? So what we do during steel making, like we add a higher amount of manganese. So what manganese does is like it has a more affinity towards sulfur than iron, so it forms this kind of globules. So it forms these globules inside these grains, not at the boundaries, and thus it reduces the susceptibility of this steel to form cracks at the boundaries and leading to their propagation through boundaries, and thus avoid any brittle failure or a catastrophic failure. Now another thing is like you can increase the fracture resistance of a material by introducing a compressive stress on the surface. Let's understand this. We have this crack and we know that sigma f can be found out using this relation where A is nothing but this crack length. Let's say I have considered it as a surface crack. So what I do is that I put a compressive stress on this crack, and what it does is like you can find out this sigma f dash, that is the stress required to fracture, will be this sigma f plus this compressive stress. Let me write that down also here, sigma compressive here, and this adds up, this value will add up, and that is why you need a more amount of stress to fracture such kind of material which have compressive stresses on their surface. So it is an ideal thing that when you want to increase the fracture toughness of a material, always have compressive stresses or introduce a compressive stresses on the surface. Now how it is being done in glasses. So you can check this tempered glasses which we use as in our mobiles. This is also referred as toughened glass, and we get this kind of a compressive stresses on the surface by some thermal treatment. So how it is being done, so you can refer any standard textbook for this. So you have a glass and you heat it to some temperature, and you take this glass out and blow some air on this surface on both sides, and what happens, this layer, the surface layers, will get cooled faster as compared to the interior of the glass, and that is why you will create a compressive stresses because of this differential thermal cooling. Now that is why this is called as a tempered glass, which we obtain by some thermal treatments. And there is another way which we can make this glass tougher more effectively, that is chemically strengthened glass, which we can get it by using ion exchange. So you can find out this chemically strengthened glass, just use these keywords as Gorilla Glass and find out how they make this surface of this glass more tough. Now in case of steel, what we do is like carburization. So we increase the carbon content on the surface layers and do some heat treatment such as quenching to make the surface stronger or introduce some compressive stresses on the surface of steel. Another way is to increase the fracture toughness is like make the grains finer, so which increases the tortuosity of crack. And what do you mean by tortuosity? It's like, let's say you have this material and the crack will propagate in this fashion. I call this length, total length, to be Lm. Now what I do is that I can project this crack along this direction, and I call it as a projected length. So when I say increases tortuosity, it means the tortuosity is defined as Lm, that is total length of this crack, divided by the projected length. So if the tortuosity is higher, that means the crack takes a more path or more length, that Lm is more as compared to Lp. And fine grain does increase this tortuosity, and thus you get an increase in the fracture toughness. With this, I'm stopping topic of fracture. Thank you.